Download this code from codegive.com, link in the description below. OK, let's dive into Hoare logic's rule for while loops, a crucial component of formal verification for programs. This will be a detailed tutorial with explanations, examples, and code snippets to illustrate the concepts. Module 186, Hoare logic rule for while loops. 1. Introduction, Hoare logic and program verification. Hoare logic, also known as floyd-hoare logic, is a formal system for reasoning about the correctness of computer programs. It provides a set of axioms and inference rules to formally prove that a program satisfies its specification. The key idea is to associate assertions, logical statements, with program points. These assertions describe the state of the program variables at those points. Hoare triple *. The fundamental building block of Hoare logic is the Hoare triple, PCQ. P is the precondition, an assertion that must be true before the execution of the code segment C. C is the code segment, example a statement, a sequence of statements, a loop. Q is the postcondition, an assertion that must be true after the execution of the code segment C, assuming that the precondition P was true before the execution. Validity of a Hoare triple *. The Hoare triple PCQ is considered valid if, whenever P is true before the execution of C, and C terminates, then Q is guaranteed to be true after the execution of C. Partial versus total correctness *. Partial correctness *. If PCQ is valid, and C terminates, then Q holds. Partial correctness doesn't guarantee termination. Total correctness * guarantees both partial correctness and termination. To prove total correctness, you need to prove that the loop terminates in addition to showing that the Hoare triple holds. 2. The rule for while loops. The core of this module is the Hoare logic rule for while loops. It's a bit more complex than rules for simple assignments or sequencing, but understanding it is crucial. The while rule looks like this. Formally, let's break this down. Invariant, the loop invariant is an assertion that must be true before the loop starts, at the beginning of each iteration of the loop, and after the loop finishes. It's the cornerstone of reasoning about while loops. Finding a suitable invariant is often the most challenging part of proving the correctness of a loop. Condition *. This is the Boolean expression that controls the execution of the loop. The loop continues to execute as long as condition is true. Body *. The code that is executed in each iteration of the loop. I condition body I*. This is the crucial part. It says that if the invariant I is true and the loop condition is true before executing the loop body, then after executing the body, the invariant I must still be true. In other words, executing the body one time preserves the invariant. I while, condition, body I condition *. This is the conclusion. If the invariant I holds before the loop, and the body preserves the invariant, then after the loop terminates, both the invariant I and the negation of the condition, i.e., condition, will be true. The condition is true because the loop terminates only when the condition becomes false. Intuition behind the rule *. Think of the invariant as a bridge that connects the state of the program before the loop to the state of the program after the loop. The body of the loop might change the values of variables, but the invariant remains true. Because the invariant holds at every iteration, we can use it to reason about the overall effect of the loop. 3. Steps to applying the while rule. Here's a general approach to using the while loop rule to prove correctness. 1. Choose a suitable invariant. This is the most important and often the most difficult step. The invariant should capture the essential relationship between the variables that the loop manipulates. it should be asterisk true before the loop starts, asterisk the initial state should satisfy the invariant. Asterisk preserved by the loop body, asterisk if the invariant is true before executing the loop body, it must be true after executing the loop body, assuming the loop condition is also true. Asterisk strong enough to imply the post condition, asterisk when combined with the negation of the loop condition, the invariant should imply the desired post condition. To prove the invariant is initially true, asterisk show that the invariant I holds before the loop begins. This is typically done by showing that precondition equals I, the precondition implies the invariant. 3. Prove the invariant is preserved, asterisk show that I condition body I is valid. This is the core of the proof. You need to demonstrate that executing the body of the loop when I and condition are true leaves I true. This usually involves applying other Hoare logic rules, example the assignment rule, to the body of the loop. 4. Show that I condition equals post condition, asterisk demonstrate that when the loop terminates, the invariant I and the negation of the loop condition together imply the desired post condition. 4. Example, calculating the factorial. Let's consider a simple example, calculating the factorial of a number using a while loop. We want to prove that this code correctly calculates the factorial. Here's how we can use Hoare logic to do it. Asterisk precondition, Pn equals 0, we assume the input n is non-negative. Asterisk post condition, Q fact equals n, after the loop, fact should be equal to the factorial of n. Asterisk loop invariant, I1 equals n plus 1 fact equals I1, this is the crucial part. Let's break it down. Asterisk 1 equals n plus 1, I is always within a certain range, important for termination. Asterisk fact equals I1, fact holds the factorial of I1 at each iteration. Now, let's follow the steps to prove the correctness. 1. Invariant is initially true, asterisk before the loop, I equals 1 and fact equals 1. Asterisk so, 1 equals I equals n plus 1 becomes 1 equals n plus 1, which is true since n equals 0. Asterisk and fact equals I1, becomes 1 equals 1 to 1, which is 1 equals 0, which is 1 equals 1, which is true. Asterisk therefore, I is initially true. N equals 0, I equals 1, fact equals 1, I. 2. Invariant is preserved, asterisk we need to prove I equals n, fact asterisk I equals I plus 1, I. Let's analyze the loop body. Asterisk assume I equals n, is true. That is, 1 equals I equals n plus 1 fact equals I1. I equals n. Since I equals n and I equals n plus 1, we can infer I equals n. Asterisk fact asterisk I, let's use the assignment rule. After this assignment, fact becomes fact asterisk I, so the assertion is fact equals I1. Asterisk I, where fact is the new value of fact. Using the definition of factorial, fact equals I. Asterisk I equals I plus 1, again using the assignment rule, after this assignment, I becomes I plus 1. Let I be the new value of I. So, the assertion is now, fact equals I dash 1, and 1 equals I equals n plus 1. Substituting I plus 1 for I we get fact equals I plus 1, dash 1, and 1 equals I plus 1 equals n plus 1, which implies fact equals I, and 0 equals I equals n. Since we already know that I equals n and fact equals I, the invariant I remains true after executing the loop body. Therefore, we have proven that I equals n, fact equals fact asterisk I equals I plus 1, I. 3, I condition, equals post condition asterisk we need to prove that, 1 equals I equals n plus 1 fact equals I1. I equals n, implies fact equals n. Asterisk, I equals n, is equivalent to in. Asterisk we also have I equals n plus 1. Asterisk combining in and I equals n plus 1, we get I equals n plus 1. Asterisk substituting I equals n plus 1 into fact equals I1, we get fact equals n plus 1 dash 1, which simplifies to fact equals n. Asterisk therefore, I condition, equals fact equals n, is true. Conclusion asterisk. We have successfully proven that the factorial function calculates the factorial of n correctly, assuming n equals 0, using Hoare logic. 5. Code example, Python. Here's a similar example in Python. The Hoare logic proof would be identical to the Java example, just adapting the syntax. 6. Common mistakes and challenges. Asterisk finding the correct invariant asterisk this is often the hardest part. There's no magic formula. It often requires careful reasoning about what relationships between variables are maintained by the loop. Sometimes, you might need to strengthen an initial guess of the invariant to make it work. Asterisk proving preservation of the invariant asterisk this can be tedious, involving careful application of other Hoare logic rules. Asterisk termination asterisk Hoare logic by itself does not guarantee termination. To prove total correctness, you need to show that the loop terminates in addition to showing the Hoare triple PCQ holds. For example, you can prove termination by finding a variant function that decreases with each iteration and is bounded below. Asterisk dealing with complex loops asterisk for more complex loops, example nested loops, loops with multiple exit points, the Hoare logic proofs can become very intricate. 7. Importance and applications. Hoare logic is a fundamental tool in asterisk formal verification asterisk it provides a rigorous way to prove that software meets its specifications. Asterisk compiler optimization asterisk compilers can use Hoare logic to reason about program behavior and perform optimizations that preserve correctness. Asterisk program understanding asterisk the process of constructing a Hoare logic proof can greatly enhance understanding of how a program works. Asterisk software engineering asterisk it provides a framework for designing programs with correctness in mind from the outset. 8. Summary. Asterisk Hoare logic provides a way to formally specify and verify programs. Asterisk the Hoare triple PCQ expresses a claim about the effect of a code segment C. Asterisk the while rule is, I condition body I slash I while, condition, body I condition. Asterisk the loop invariant I is the key to reasoning about while loops. Asterisk to prove correctness, you need to show that the invariant is initially true, preserved by the loop body, and strong enough to imply the post condition when combined with the negation of the loop condition. This detailed explanation and example should give you a good grasp of the Hoare logic rule for while loops. Practice with more examples to solidify your understanding. Good luck.